Okay, this video session is about correlational designs. Most people are familiar with the idea of correlations, meaning that two pieces of information or two pieces of data are related to one another. And basically, you can have two kinds of correlations. Actually, there's three. There is a positive correlation, means as one number goes up, the other number goes up. There's a negative correlation, which means that as one number goes up, the other one goes down. The other correlation is there's no correlation. There's no relationship between two pieces of data. Most people understand the concept that two pieces of information can be related, but what they don't get is this. Just because they're related to each other, that does not indicate a cause and effect relationship. And that's one of the biggest mistakes that people make with correlations. They think that by one number going up, that is causing the other number to going up. That's not true. It's just a relationship between the two. The advantage of these correlational designs, it allows for independent variables over which researchers have no control to be studied. For example, gender and mathematics. You don't have any control over whether or not somebody's male or female, but you can look at that as a piece of information. Allows you to explore possible relationships in terms of trying to find further investigations. For example, going back to the relationship between school district size and PSAT scores, we might start out as a correlation between district size and those, but that's just really leading us to the next part of, okay, if there's a relationship, how can we better define that relationship? And we do that with other statistical tests. Reminder on types of data, and this is important because it influences which test you get to pick. Ordinal data means they're ranked. For example, junior, freshman, sophomore, junior, senior. Survey data is ranked data. Raw scores like dollars earned, years of experience, that kind of thing. Many test scores they're just interval ratio data. Nominal means it's just a classification. Male, female, Republican, Democrat, dichotomous, yes, no. And this type of information influences the type of correlation in terms of which one we pick. If the data is a ratio or interval, both pieces of data, then you use something called a Pearson's correlation. If one or both of the pieces of data is categorical, ordinal, nominal, the other test is called a Spearman's rank order. What you get, what's called an R value, is the same. It doesn't matter which one of these you run. They're just different paths to getting that same value. So whether you run the Pearsons or the Spearmans, you're going to get an R score. That R score, the value of it, whether it's a strong positive or weak negative, that doesn't change depending on which test you run. But you got to pick the right test. All right, some basics of this. As we said, the correlation is the degree to which two variables are related, and they can the range anywhere from a perfect -1, which means a perfect negative correlation, to a perfect positive correlation. And right in the middle of that is 0, means no correlation at all. A couple of examples: kindergartners' fall and spring literacy. There tends to be a very positive, strong correlation of 0.8. So the scores that they get in the fall on their literacy tends to have a whole lot to do with scores they get in the spring. Makes sense. As opposed to something like time spent watching television and grades. If you spend a lot of time watching television, you're going to have lower grades on your courses, on your exams. So there's a negative relationship, negative 0.21. Several other examples. Reading comprehension, these are all positive correlations. Kindergartners' internal behavior problems, and in literacy, negative correlations. What I want you to notice about these, though, is we've not gotten into the important component of significant relationships. I want to show you an example of that in just a minute. So let's look at a real brief example. If I were to collect two sets of data, in this case, years of experience and income in thousands of dollars. So, for example, subject 1 has 0 years of experience. They make $20,000 a year. Subject 2 has 5 years. They make $30,000. On and on and on. there's a lot of information included, and it comes in the form of interval data or ratio data. And really, there's only one comparison that we can make. We can only really look at the relationship between the number of years of experience they have and how much money they make. So we punch a couple of buttons in SPSS, and we get this. 1 year of experience is 20,000. 5 years, we had one that's making 30,000. 5 years, we had one making 40,000. So you end up with this pattern like this. And there's a line that runs through this. This is going back to high school math, called a line of best fit. And this is a visual representation of something. But that's not enough. We need something else. We need to be able to make better use of our data. We need something called an R value and the level of significance. So going back to this, its R value is 0.858, and that is a significant relationship. It is possible that you can have a very high R value, but it's not a significant relationship. It's possible that you could have a very low R value, like I've seen an R value of 0.2 that's a significant relationship. So these two numbers go together. This R squared is something called explained variance. And what that means is if you take R, the 0.858, and square it, multiply it by itself, you get this number. And what that is telling us is that the relationship between income and years of experiences is a significant relationship. And that relationship, just by those two things, is defined, is 74% defined, or 0.74. Something about that relationship, though, is not defined. That's called unexplained variance. 26% of that relationship is explained by something that we didn't control for. That goes back to the cause and effect relationship. Just because two things are related, that doesn't indicate a cause and effect. There are other things contributing to that relationship. And because we cannot account for that here, we don't know what it is. As I said, it's important to remember that just because a correlation occurred, that does not make it significant. You need both pieces of information. And we're always still looking for less than 0.05 for a significant relationship. And I'll provide some examples when this is over with of what that would look like. Following this slide, there are several presentations, and after you go through this video, I want you to go back and look at this. There is strong negative correlations, no correlation, strong positive, weak negatives, and weak positives. So you can look at a visual representation plus the R value. So for example, here all the data is just scattered out. There is no relationship between what is happening on this side and this side. Here's a visual representation of what is happening when, as this number goes up, this number goes up. That's positive correlation. As this number goes up, this number goes down. That's a negative correlation. But how will they fit together? It contributes to the strength of the relationship. As you'll see, there's a perfect relationship here. All the dots, all the pieces of the data fall on the line of best fit. Here, they don't fit quite as well. And as that number goes down, they fit less and less well to the point that they don't fit together at all. Now, going back to the cause and effect, this is the relationship between the global average temperature of the planet and the number of pirates in the world. And as you can see, there is a positive correlation between the number of pirates in the world and the average temperature. So I often ask people in the class, if you wanted to lower the average temperature, what would you do? Well, obviously from this, you would need to have more pirates in the world, which isn't true. This is an example of a relationship between two sets of numbers that have no cause and effect at all. They just happen to be related, but it didn't have anything to do with another. You can't lower the average temperature of the Earth by having more pirates. That is a prime example of a mistake people make of trying to introduce a cause and effect relationship. Now, here's some other ones. There are positive correlations between ice cream consumption and drowning. There are positive correlations between ice cream consumption and murder. There are positive correlations between ice cream consumption and boating accidents. And there are positive correlations between ice cream consumption and shark attacks. What this is going to be part of your discussion thread. So that will show up again later. And that's about it. We will have some practice examples available for you so that you can see what these look like and how to interpret it. It's quite a bit easier to interpret than something like an ANOVA or analysis covariance. And we'll make that available to you, and it'll be included in Module 6 as well.